Good morning. Today we are going to walk through some common stumbling blocks for roughly the first half of Unit 2 for the AP Physics 1 curriculum, specifically forces and Newton's three laws.
Flippin' physics.
First, realize the center of mass of an object is not necessarily a physical location on the object. The center of mass of an object is the mass-weighted average position of all the mass within an object. Therefore, the center of mass of an object can be physically outside the object. For example, a banana, a horseshoe, a golf club, or a donut.
Or for a two-object system like the Earth and the Moon, right, Mr. P?
Actually, the idea is correct. However, the Earth is so much more massive than the Moon that the center of mass of the Earth-Moon system is located roughly 1,700 kilometers below the surface of the Earth.
Oh, right. That makes sense.
Good. Now, I'm going to ask y'all a few questions. Can an object moving at a constant velocity have more than one force acting on it?
Yes. However, those forces must balance out to cause a net force of 0 on the object. That will make the acceleration of the object 0 and mean the object is moving at a constant velocity.
Oh, right. The net force acting on the object equals mass times acceleration. So if the object is moving and the net force acting on the object equals 0, the acceleration of the object is 0, and the object is moving at a constant velocity.
That is what I said.
Eh.
That is called translational equilibrium.
Right.
Right. Next, can an object move at a constant velocity and have zero forces acting on it?
Yes. If there are zero forces acting on an object which is moving, the net force acting on the object is 0, so again, the acceleration of the object is 0, and the object is moving with a constant velocity.
Correct. Next, can an object move at a constant velocity and have only one force acting on it?
If there is only one force acting on an object, then the net force, the sum of all the forces, cannot be equal to 0. Without another force to counteract the one force, the net force cannot be 0, so the acceleration of the object cannot be 0, so the velocity of the object has to change. So, no, it is impossible for an object with only one force acting on it to move at a constant velocity.
Yep. Next, does a moving object have to have a force acting on it in the same direction as its velocity?
What?
When an object is moving, its velocity is pointed in a certain direction. Does the object have to have a force acting on it in the same direction as the direction of the velocity of the object?
Okay, so now I understand the question. No, right?
Right.
Right. For example, a hockey puck sliding to the right and slowing down has a velocity to the right, and the forces acting on the hockey puck are a force of kinetic friction to the left, an upward force normal, and a downward force of gravity. None of those forces are in the same direction as the direction of the velocity of the hockey puck, so no. A moving object does not have to have a force acting on it in the same direction as its velocity.
Right.
Correct. One more question. Are the force normal and force of gravity acting on an object always equal in magnitude?
No.
Yes.
No, this is only true when the upward force normal and the downward force of gravity are the only forces acting on the object in the y direction, and the object is not accelerating in the y direction.
Right. Thanks.
It is not only true then. There are lots of other examples where the force normal and force of gravity acting on an object are equal in magnitude.
Like what?
An object on a ceiling being pushed upward with an applied force which has twice the magnitude as the force of gravity.
And an object on a 60-degree incline with a force applied down and perpendicular to the incline, which has a magnitude which equals half the magnitude of the force of gravity.
Okay, fine. The place where we see this most often, and therefore why we often think the magnitude of the force normal and force of gravity acting on an object are the same, is when the upward force normal and the downward force of gravity are the only forces acting on the object in the y direction, and the object is not accelerating in the y direction.
Agreed.
Sure.
Thank you all.
Yeah.
Next, weight and mass are not the same. If you have any questions about this, I have an entire video for you.
Bo, do you remember being in the elevator for that one?
Yep.
Yeah.
And On an incline, the component of the force of gravity which is parallel to the incline, which we call the force of gravity parallel, is always directed down the incline. There are very few alwayses in physics, however, this is one. The force of gravity parallel is always directed down the incline. Billy, if you were not really paying attention in this class, what might you tell me Newton's second law is?
Oh, I've got this one.
Yeah.
Force equals mass times acceleration.
Yep. And Bo, considering you are not some riffraff member of the regular populace, you are a flipping physics student, what is Newton's second law?
Net force equals mass times acceleration, where both force and acceleration are vectors.
Yeah.
Yeah, thank you. Please remember, it is the sum of all forces which equals mass times acceleration, not just a single force. And force and acceleration are both vectors, which means they have both
Magnitude and direction.
Exactly. Now, free body diagrams. Actually, I have so much to say about free body diagrams that they deserve to have their own video, which is a free portion of my AP Physics 1 Ultimate Exam Slayer.
Is that the same as his AP Physics 1 Ultimate Review Packet?
No, the Ultimate Exam Slayer has 2 hybrid digital practice exams and resources specifically for understanding the AP Physics 1 exam, and the Ultimate Review Packet is primarily for understanding the AP Physics 1 curriculum and has 1 hybrid digital practice exam.
Okay, thanks.
You are welcome.
Yeah, thanks.
You are also welcome.
Okay, let's talk about Newton's third law. For every force object A exerts on object B exerts a force with equal magnitude but opposite direction on object A. And force is, of course, a vector. Actually, I'm going to turn this over to the three of you. What do you think common stumbling blocks are for students with regards to Newton's third law?
Absolutely. I would say that a typical stumbling block is that students may think that a more massive object applies a larger force on a less massive object, but that is not the truth. Both objects exert the same magnitude force on the other object. I mean, that is a basic premise of Newton's third law. However, it did confuse me at first.
Yeah, and another point of confusion is that even though the magnitude of the force is the same, both objects do not have the same acceleration. The object with the larger mass will have a smaller acceleration because of, Newton's second law.
Assuming the net force is the same in both cases.
Right, thanks.
You are welcome.
Another thing is that Newton's third law force pairs act on different objects. For example, the upward force of the block exerts on the disk is equal in magnitude to the downward force the disk exerts on the block. Those two forces are a Newton's third law force pair, and they act on different objects, so they are not both in the free body diagram for a single object. For example, the free body diagram of the forces on the disk are the upward force the block exerts on the disk, or the normal force from the surface on the disk, and the downward force of gravity acting on the disk. And the free body diagram of the forces acting on the block are the downward force from the disk on the block, the downward force of gravity on the block, and the upward force from the table on the block, or the normal force from the surface on the block.
Right. Just to be clear, the Newton's third law force pair here is the upward force the block exerts on the disk, and the downward force the disk exerts on the block. And the point is that those two forces act on two different objects. Okay, another thing. Both of these forces act at the same time. It is not one force and then another force. It is not an action and then a reaction. Both forces act at the same time. Next up, free fall. There is only one force acting on an object in free fall. That force is the force of gravity, and it is always directed straight toward the center of the planet, which is, by definition, always downward.
Wait,
Yes, Billy?
what if the object is moving upward in free fall?
The force of gravity is still down. The force of gravity accelerates the object downward. The force of gravity slows the speed of the object down as it moves upward.
Oh.
What about when it is at the top of its path and the velocity of the object is 0 for a moment?
Yes, the force of gravity is still acting downward on it when it is at the top of its path. The force of gravity accelerates the object downward and is what switches the object's velocity from upward to downward, and the velocity of the object is momentarily 0 when switching from positive to negative.
Right. In fact, if you look at the free body diagram of an object in free fall, the net force in the y direction equals the negative of the force of gravity. Negative because that force of gravity is down. And the net force in the y direction equals mass times acceleration in the y direction. Substituting mass times gravitational field strength in for force of gravity means
Everybody brought mass to the party.
Everybody brought mass.
we can be equitable and take the same mass from everyone, and we get that the acceleration in the y direction of an object in free fall equals the negative of the gravitational field strength of the planet, which we already knew, but it is great to be able to prove.
Cool.
Nice.
Sure.
Thank you very much for learning with me today. I enjoyed learning with you.